And we left off almost to the end of renal balance part 1, okay? And just to kind of summarize some of the things we talked about at the initial, at the beginning of this packet, we talked about the idea of fluid balance, so input matching output, that is input and production matching output and consumption. We also spoke a lot about the ways that water is reabsorbed. So throughout the beginning of this packet, we reiterated this idea that water is reabsorbed at the proximal tubule via the solute reabsorption first. So a lot of it, most of it is reabsorbed in the proximal tubule via solute reabsorption. And then as we get into the loop of Henle, the mechanism is different here as well. It's still unregulated, right? It's still unregulated, but the mechanism is different. We had this counter current multiplier mechanism. And so what we saw was that water exclusively is reabsorbed down the descending limb, and then up the ascending limb, solutes are exclusively actively pumped across that membrane. And so that allowed for this, this gradient, this medullary osmotic gradient, where deeper in the medulla, the interstitial fluid along with the tubular fluid. So really important to make that connection. Both the interstitial fluid and the tubular fluid are at a high osmolarity, right? Really concentrated, a lot of solutes in that solution. As we go back to the cortex, or the peripheral parts of the kidney, the cortex where we have the loops and so on, not the loops, the proximal and distal tubule, we have the interstitial fluid and the tubular fluid being at a lower osmolarity, so less solutes dissolved. Okay, and we talked about why that was so important. We're really trying to concentrate the urine here. And so having that descent down into that salty part of the medulla and then coming all the way back up to the cortex is what helps us to really concentrate the urine by creating a lower fluid osmolarity when we get back up to the distal part of that loop, okay? And we kind of went through this example of how we set up that gradient and then talked at length about how we maintain that gradient, right? We've got active movement of solutes on one end and water only on the other end. Okay, let's continue on here by speaking a little bit about the overall water reabsorption, so how it differs in the proximal tubule and then in some of the later parts of the tubule. So we said 70% of that water is reabsorbed in the proximal tubule. This is not regulated. And this is different from that 99% that we spoke about. So when we spoke about the proximal tubule, we said that 99% of the water that came through there was reabsorbed. This 70% is 70% of the total water reabsorbed in the kidney overall. So 70% of that is happening in the proximal tubule, and that is in an unregulated fashion. So no hormones are going to influence that. Our hydration status is not going to influence that. That is going to happen freely as long as we have solute moving across that, that epithelial and endothelial membrane. The other 20% is somewhat mixed. So 20% of it happens according to the later parts of the tubule. So that is the distal tubule, but then it's also sort of incorporating what's happening at the descending limb of the loop of Henle. The distal tubule is going to be regulated by ADH, so antidiuretic hormone. We'll talk about that in a minute. But the loop is unregulated as well. So the loop, although it's kind of lumped in that 20%, is not regulated, whereas the distal tubule, so the distal part of that convoluted tubule, is regulated by ADH. And then the final 10% happens via the collecting duct, so the very distal parts of the tubule, and that is also regulated by antidiuretic hormone. Which is going to, change depending on our hydration and volume status. Okay. So the osmotic gradient that we establish is really going to determine the amount of water that is reabsorbed in the distal tubule and the collecting duct. Depending on what the osmolarity of that filtrate looks like when we get to the final part of that loop, that will determine how much we have reabsorption thereafter, right? It's also going to be dependent upon the permeability of water, and the permeability of water in the distal tubule is regulated in that we can insert more of these water channels. So it's not happening freely the way that we spoke about it across the proximal tubule, but it's happening according to the permeability. And we made this connection in last semester that the permeability is really a reflection of how many channels are existing in the membrane. So we've got these aquaporins, which are these water channels. And if we put more of them in the membrane is more permeable to water. If we put less of them in the membrane is less permeable to water. And so we can regulate how much water. This is another way that we can regulate water reabsorption in the distal tubule by inserting more or less of these aquaporin channels in order to reabsorb more or less water. Okay, aquaporin 3 is exclusively in the basolateral membrane always. Aquaporin 2 is present in the apical surface only. And it's basically they're basically going to be inserted in response, aquaporin 2 that is, going to be inserted in response to ADH. So I'll talk about how ADH gets secreted in a moment, but when ADH is secreted, it's going to stimulate the cells to insert more of the aquaporin 2 channels only into the apical side of the membrane, whereas aquaporin 3 channels are always located in the basolateral surface. Okay. All right. So when the membrane is impermeable to water, that is the distal tubule and the collecting duct, when it is impermeable to water, this simply means that water cannot leave the tubules. So it's going to be lost as a part of that filtrate. It's going to be excreted as a part of the urine because we cannot move it back into the vascular structures because we cannot reabsorb it. So if there's no aquaporin channels, water cannot leave the tubule, we cannot reabsorb that water, and more of it is going to be lost into the urine. And so ADH stimulation is going to help to insert those aquaporin channels, specifically aquaporin 2, into the apical side of the membrane. And that is going to help to reabsorb or reclaim more of that water. And so it's going to prevent the water from being extremely diluted. It's going to help to concentrate the urine as well. So if we can pull more of that water from our filtrate, we can also help to concentrate the urine and to increase the urine osmolarity, and to lose only waste and reclaim most of that water, especially if it's needed. So we'll see some of the stimuli for ADH, but basically if there is loss of water, if there's low blood volume, if the body is dehydrated, we're going to have more ADH secreted so that we can reclaim or reabsorb more of that water by inserting those aquaporin 2 channels and allowing for water to be reabsorbed. Okay. Now, the maximum amount of water being reabsorbed depends on the length of the loop of Henle. We made this connection before. So if we have a really long loop of Henle, we have more time to really manipulate the osmolarity of that filtrate. And so we're going to have more concentrated urine. If we have a shorter loop of Henle, we're going to have less time for that ability to manipulate the filtrate, and we're going to have less concentrated urine. This is why we have animals like desert rats and camels that have really long loops of Henle because they don't have ready access to water. And so they really want to help to conserve as much water as they can by really concentrating that urine. And so having a really long loop of Henle helps to do that. All right. So this is just comparing what the urine output would look like depending on the osmolarity of our filtrate and the ability to reabsorb water. So on the left, we're looking at a really high urine volume with a low osmolarity. This is if you're well hydrated, if you're drinking lots of water, if you're in a good hydrated, status. Your tubular fluid comes out at 100, and then throughout the distal part of the tubule and the collecting duct, you're not going to reabsorb much of that water because your body doesn't need much of that water. You don't have a lot of ADH being circulated, right? You don't need to reabsorb much of that water. You don't have a lot of aquaporin 2 channels inserted in the membrane here. And so the osmolarity is going to pretty much stay at 100, and you're going to be able to lose a little bit more fluid because you're in a good hydrated, well hydrated status. You're also going to have higher volume of that urine. And we kind of made this connection before. If you're well hydrated, you have a high volume of urine output, but it's also more diluted, more clear as, as is needed because you're not reabsorbing or concentrating that urine as much. On the other end here, so in the image B, this is what's happening if you're really extremely dehydrated, okay? The most obvious difference is that this is really yellow, right? That's indicating that it's really concentrated and it's mostly waste. mostly solutes, mostly waste, extremely concentrated. It has a really high osmolarity because this scenario, the body is in an extremely dehydrated state. Maybe there's some type of hemorrhaging, maybe there's, extreme exhaustion from exercise or, sweating vigorously. And so you're reclaiming a lot of water here by inserting more of those aquaporin 2 channels to help that reabsorption process, to bring that water back into the vasculature. And so what you're left with in terms of your urine, in terms of that filtrate, is mostly waste, mostly solutes. And we talked about the fact that you have to lose at least 400 milliliters per day. That is that obligatory loss in order to excrete toxins and waste products. The body must eliminate at least 400 milliliters of urine to get rid of that waste. And so you're still going to have urine output, but it's going to be very low in volume. It's going to be very concentrated, have a very high osmolarity, and it's going to be mainly waste and mainly those solutes that were reabsorbed. Okay. All right. So just to reiterate this idea of that obligatory water loss, this is the minimum volume of water that must be excreted as urine per day. And that would give us about 400 in terms of the quantity, but the osmolarity of that fluid is going to be very concentrated, very lot of solids dissolved in there, mostly waste and very little water. So it's going to have an osmolarity of about 1,400 milliosmoles, and that is in an attempt to lose that waste. So the solutes must be excreted, and so we have to eliminate some bit of urine as a way to eliminate those toxins and that waste. Okay. All right. All right, let's take a pause here, see what questions we have, and then we'll look at these checkpoint questions here. All right. So let's start by looking at question 1. So where does most reabsorption occur in the renal tubules, and where does the regulation of water reabsorption occur in the renal tubules? So where does most of the reabsorption occur, and where does the regulated reabsorption occur? All right, excellent. So the proximal tubule is where we have most of the water reabsorption. Excellent. Okay, excellent. And then someone is also saying that in the distal tubules where we have the regulated reabsorption. So that is correct. And more specifically, the distal convoluted tubule along with the collecting duct. So those two structures, we're going to see that most of the, not most of, but all of the regulated reabsorption happens, whereas most of the volume, most of the water in general happens or is reabsorbed across the proximal tubule. Okay, so someone is asking me to kind of go over briefly how ADH works. We're going to talk a little bit more about ADH, so kind of reserve questions, but we're going to get into the details of how it affects those cells in terms of that second messenger, and we're going to get into some more details there. The second question here, compare the movements of solute and water across the epithelial cells, lining the descending limb of the loop of Henle and those lining the ascending limb of the loop of Henle, and then explain how this differential movement allows establishment of the osmotic gradient in the renal tubule. So a pretty loaded question, but let's take the first part. So compare the movements of solute and water across the epithelial cells lining the descending limb of the loop of Henle and the ascending limb of the loop of Henle. All right, so across the descending limb, we have the movement of water and no solutes. Across the ascending limb, we have the movement of solutes and no water, right? Across the descending limb, the mechanism there is osmosis, so it's happening according to a gradient. It's passive movement because we have a high solute concentration in the interstitial region out in the medulla, because we have a low solute concentration in our filtrate at that time. We have a water gradient in the opposite direction. So water passively moves from the descending limb across into the interstitial region. Along the ascending limb, it's the exact opposite. So we have solute only moving, and that is because of active movement. So there's a pump that's actively removing those solutes, that's sodium, chloride, and potassium. Okay. And then the second part of the question, explain how this differential movement allows establishment of the osmotic gradient in the renal medulla. So we kind of described this before. Essentially, because we're pumping solutes out along the ascending limb, we're making the medulla more salty, more concentrated. We're increasing the osmolarity of the interstitial fluid of the medulla. So by doing that, we now allow for that passive gradient of water to move along the descending limb. So that's what we mean by countercurrent. The active pumping of these solutes is facilitating the passive movement of water along the other side. All right. And the reason that that sets up a gradient is because we keep pushing more fluid down into that loop. So we do that, we pump solutes out, pump water out, we push more fluid down. Pump solutes out, pump water out, we push more fluid down. And continuing to do that, we eventually get to the steady state where the very deepest part of the medulla has the highest osmolarity, whereas the very top, where we're closest to the cortex, has the lowest osmolarity. And that holds true for both the filtrate that's being moved down the loop, along with the interstitial fluid that is around the tubular structures. Okay. All right. So basically the countercurrent multiplier mechanism is how we establish the medullary osmotic gradient. Okay. And then number 3 here, can pure water be excreted as urine? The answer is no, in short, right? We cannot excrete pure water. There must be some type of solutes present in that. And so even if we're well hydrated and we're excreting a lot of urine, it's high volume, it's very diluted, there must be a way for us to lose waste, for one, but also solutes that were not reabsorbed, that are still moving through the tubular structures. And so that urine, that end product there, will have an osmolarity of something. It will not be an osmolarity of 0. It will not be pure water. Okay, there will be some solutes. However little, there will be some solutes dissolved there.